では、イゴールさん、お願いします。
Igor, floor is yours.
Good afternoon, everyone. First, I would like to thank you, the organizers, for inviting me here. And thank you for everyone for coming to listen to my talk. I will talk about a chip in recent Intel motherboards that is, okay, well, let me explain it later. First, what we will talk about, I will talk about what is this chip, what does it do on the high level. Then I will cover some of the low-level details, how it works inside, what software it runs, how it's structured, and how to analyze it. Then I will discuss some of the security features of this chip, because it does use some security countermeasures, and possible attacks against it, and what came out of those attacks. Then I will talk about one of the components of this chip in more detail, and we'll conclude with some results. So a little about myself. I'm really interested in software reverse engineering for about 15 years already. I've been using software called IDA, Interactive Assembler, for a long time. And in 2008, I joined actually the company that makes this software. So since then, I've been working on developing this software, IDA, and the Hexaresty compiler. But not just developing, I also do all other things, technical support, trainings, and everything. I have a bit of interest in embedded devices. So I had some experience of hacking devices like Kindle or Sony Reader. But recently, I'm more interested in how the PC works on the low level. So things like BIOS, UEFI, and in this case, the ME management engine. I'm also moderating the reverse engineering subreddit. So if you're interested in reverse engineering, this is, I think, is pretty good source of information. Now, what is actually this management engine? So management engine is a chip, is a microcontroller, which is embedded inside all recent chipsets from Intel. This chip is intended for management purposes originally. And that's why originally it was residing in the network card. But later it was moved for better integration, for better connectivity with the processor. It was moved in the chipset, in the actual chipset. It shares the flash code space, the flash space with the BIOS. So you have the BIOS code and the ME code on the same flash chip. But it runs completely independently from the main CPU. So for example, even if your system is hibernating or you turned it off, but it is still connected to the power, this chip, this management engine, can be still active. And it has a dedicated connection to the network interface. So all the network traffic to or from it can bypass the main CPU, and it can communicate with the network without the main CPU knowledge. So this is a diagram from some Intel documentation. It's a bit outdated, but you can see that this is the microcontroller which resides in this case, graphic and memory controller hub. It's the old kind of the chipset. And inside it runs the thread X kernel. Then there are some abstraction level and various interfaces provided by this software. And then on the hardware side, it has interfaces with the host. It has interfaces to the network and various built-in peripherals for crypto, for non-volatile memory. And it also has connection, of course, to the flash chip. Now, this how does it communicate with the outside world? It has two connections. It has connection to the host CPU, by which it can communicate with the OS with various drivers. And this connection is called the host embedded control interface previously, and now it's called management engine interface, MEE. And this interface works over the PCI bus. There is an additional interface that it can use, which is network-based. And this interface uses a dedicated connection to the network chip that this management engine has. So with this network connection, it can bypass the main CPU and communicate with the outside world. This protocol is based on the SOAP, XML-based. It can be plain text HTTP or encrypted HTTP, depending on the settings or on the generation of the firmware. Now, what components are inside this management engine? Some of the features that it can provide. So the one that it was originally made for is the active management technology. It provides remote configuration, administration, repair. So this feature allows the administrator to connect remotely to the PC and completely control it if necessary. For example, it can be rebooted, it can be reinstalled, and everything. System defense. Administrators can add various firewall rules to this management engine, and it will act as a very low-level firewall. So even before the operating system, the packets will be checked and maybe some countermeasures taken. IDE redirection and serial overrun. These features allow administrator to remotely boot a disk image, for example, for this computer. So this allows reinstallation, reimaging of the PCs, and so on. Identity protection in recent versions. It embeds one-time password functionality for two-factor authentication. So for example, instead of the smart card or a USB dongle, you may use this functionality built in this chip. And the protected transaction display allows secure communication with the remote host without it being intercepted by the host CPU. So this, for example, you can enter PIN and no malware, no any host software can intercept this communication. Anti-theft feature also are possible in recent versions. For example, it can be set up that PC has to connect every now and then, for example, day, to a remote server. And if it fails to connect, then it possibly means that it's been stolen. Or maybe it has been reported as stolen, and on the next connect, the system is disabled. So in some implementations, it's even possible to disable the PC by sending a special SMS. And then to reactivate it, you need to get a password from the service. So this allows very convenient anti-theft measures. Now let's talk about how it works on the low level. So there is not much information about how it's implemented in the low level, but I managed to find some. There are some Intel's white papers. They don't talk about, they don't go much into detail, but they often mention various small details. For example, on the previous diagram, there was mentioned that the ThreadX operating system is used on inside this chip. So such small details may be gleaned from the white papers. And also patents, Intel patents, they often offer some information about how it works internally. Then, of course, Intel provides various drivers and software that communicates with this management engine. And by reverse engineering, for example, those drivers, or sometimes some code is even open source, you can have some hints of how this software, how this chip works inside. So, for example, I looked at the driver, host embedded control interface driver. I looked at the various services that are bundled with those drivers, and various utilities provided by Intel. Linux drivers, because Linux is open source operating system, and it's using GPL license. All the source of all drivers must be open, and so Intel has open source drivers for Linux. And by looking at those drivers, you can also get some hints of how it works. And then also the BIOS updates for the motherboards. So even though this firmware for this management engine, it's not updatable using normal BIOS updates. However, it's usually still included in this BIOS image. So even though it's not part of the BIOS update, it's still present there. And so you can extract it and you can look at it and you can figure out how it works. And in some cases, some manufacturers provide separate firmware updates, and so we can look at those and see how they work. Other things, there is something that Intel provides to OEMs, to the makers of motherboards, which are called ME firmware kit. So this contain various very low-level information about ME that are intended for the actual makers of motherboards, of BIOS. So these are not supposed to be distributed to end users. However, many vendors, they're a bit lazy. They don't want to do too much work. So they, instead of extracting just the drivers, they put everything on the CD or everything on their FTP site. And so you can download it, and you have all the documentation from Intel, all the tools and everything. So just if you know some keywords, for example, here you can see highlighted Flash Image Toolkit. You just enter it at Google, and you can have many hits and many hints and get interesting things. Now, since last year, you don't have to do that anymore, because Intel has released something called firmware support package. They're trying to be more open, trying to release more information about their hardware. So this package, it provides low-level initialization code for example, writing bootloaders or BIOSes. It's downloadable from Intel side, and it includes the complete set of documentation, tools, and firmware. However, they forgot to remove the confidential markings, so you have to be careful when reading it. But still, it's freely available. Now, I mentioned that ME and the BIOS share the flash space, and this is how it's implemented. So in the beginning of the flash, on the bottom, there is a region called flash descriptor region, which is basically like a partition table. So it describes the location and sizes of all other regions. And for example, the typical layout is like this. So you have a region for network interface, region 3, gigabit Ethernet. Then you have region 2 for the Intel ME code. And the last region at the top of the flash chip is the BIOS region, which contains the BIOS code. Now, this descriptor region, it contains not only the sizes and location of the other partitions, but it also contains permissions. So, for example, it can say that if the access comes from the BIOS, then it may not access the Intel ME region. So this is enforced by the chipset by using the settings, the bits in this descriptor region. So this is an additional security feature used as a countermeasure against unauthorized access to this ME region. Now, the ME region itself is not just a single block. It is structured in itself. And this is the high-level structure of this ME region. So it contains a partition table in the beginning, and then the various partitions. So these partitions, they have names, 4-character names. And here I mentioned them as some examples. For example, FOVD, I don't know what it means. EFFS is probably embedded flash file system. And then two typical partitions that may be encountered is FTPR and NFTP. And they contain the actual code which executes on this management engine. And in turn, this code partition as well is structured. So it has a header with version numbers, with the size, with the flags and everything, and contains also the public key and signature of the whole manifest header. So this signature includes, you see that I shaded in dark blue the parts which are signed. And so the signature allows the chip, the hardware, to detect all tampering, all changes in the code content. And so in this way, it's pretty difficult to change the code and make it execute your own code. So all the firmware from Intel is signed by their RSA key and cannot be changed. Now you may ask if it's only the header is signed and the data itself is not signed, why I cannot change it? Because you cannot change it because the header of every module, it contains the hash of the data. And so if you change the data, which is by itself is not signed, the hash will be changed. And so the hash will not match the one in the header. And so in this case, tampering will be detected. Now I analyzed many different versions of the ME firmware. And it seems that there have been two generations, so to speak. And they have different they use different instruction set. They use different layout of the firmware parts of the code partitions. And so here I just mentioned a bit, summarize their differences. For example, in the first generation, it seems they used an Arctangent A4 processor core with a 32-bit instruction set. And in second generation, it seems they switched to ARC 600 or something similar, which uses ARC compact instruction set, which is mixed 32-bit or 16-bit. And also, in the new generation, generation 2, they started using Huffman compression for the modules, which I will talk about a bit later. So just to mention that most of the following information is related only to generation 2. because this is more modern chipsets and they're more interesting to analyze and to work on than something old. Now here's a list of some of the typical modules that you may find in these firmwares. Every module has a name. So this may hint also on its functionality. So for example, the BUP apparently means bring up, which does various initial hardware initialization and configuration. Then there is the kernel module, which implements the scheduler that schedules all other tasks, and it provides some various low-level APIs for other modules. The policy module does some secondary initialization and provides some other APIs for other modules. Hostcom handles the communication with the host over the PCI, over the host embedded control interface. Then CLS is capability licensing service. So this implements a feature in Intel boards where you may buy so-called software upgrades. So you buy a system which is low-end, and then by buying special code from Intel, you enter this code in the software, and you can upgrade your hardware to the higher functionality. So without changing the physical hardware, you can change it in software, so to speak. So this is just apparently implemented as some software locking, which can be unlocked by using this module. So this may be interesting target to analyze, but I have not concentrated on that one. Then TDT, self-deterrence technology, which is the old name of the anti-theft, protected audio-video path, and something called JOM, which I don't know what it stands for, but it's probably something to do with Java, which implements a dynamic application loader, and I will talk about this in more detail a little later. Now, one difficulty that I encountered when analyzing firmware for this management engine is the code in ROM. So apparently, to save the flash space, there are several common routines, such as C functions, memcopy, string copy, which are not put in the firmware which is upgradable, but they're put in the on-chip ROM. So when you analyze the firmware, you don't see those functions. You see just jumps to some addresses which are not present in the code you're analyzing. So this makes reverse engineering a bit complicated because you don't see the code. You have to figure out what the missing functions does by analyzing the surrounding code. So this was a little bit difficult in the beginning. However, I found one ME image which has a partition that I haven't seen before. It was called ROMB. So what is this partition? So apparently ROMB stands for ROM bypass. And this ROM bypass allows Intel to release software upgrades, so to speak, for the early silicon, for the early hardware that they distribute to the OEMs. So when Intel is ready to release some new hardware, they first send it to the various OEMs so that they can start making motherboards, start designing them. And these early chips, they may contain various bugs. And to work around those bugs, the Intel have foreseen this functionality that allows them to override the ROM content which is embedded in the chip itself and use the ROM content from the flash chip. So this feature may be activated using Intel tools they have the functionality, they have the option called ME boot from flash. But unfortunately, so how it works, if you enable this option and you have this image with such firmware, with such ROM bypass region, then instead of executing the built-in boot ROM on the chip, the hardware jumps to the first instruction in this ROM bypass image. And this first instruction is just before the actual partition table. And it's just a single jump instruction that jumps into the code in this ROM bypass partition. So this partition is not signed, it's not verified. So whatever is in there is being executed. So this would be a nice way of executing your own code. However, it's only available on the, just a moment. It's only available on the very early silicon revisions. So you can see that, for example, here's a note that says on B0 and later, it must be set to false. So it's only available on the very early hardware. So if you just bought a motherboard in the shop, this option will not work, and it will be ignored, and you cannot execute arbitrary code inside the ME. However, still this was useful, this image was useful, because I could look at the missing pieces, at missing functions that I have not seen before, and I could have a look at basically what is inside this boot ROM on the actual chips. So for example, I found that it has C functions, it implements the ThreadX OS routines and various low-level APIs for accessing hardware. And I also have seen how it boots, basically. So after doing some low-level hardware in it, it verifies the signature of the partition, and it loads the bring up module and jumps to it. So next I thought I would have a look at the code of this bring up module, but unfortunately on the newest chipsets they use Huffman compression, and this Huffman compression uses some unknown dictionary, so I could not decompress the code. So I could not see how it works. I could not see the code that is being executed. So I will discuss a bit of some countermeasures that ME. I will return back to the Huffman compression later, but just a little bit on security and attacks that I tried. So the ME has it has multiple security features implemented. So Intel did a pretty good job here. For example, they use code signing, as I mentioned before. The signature of the code is verified, and it's only executed if the signature is successfully matched. And this is checked by the boot ROM, so you cannot easily overcome this this feature. It is signed by the Intel's key, and the hash of that key is verified, so you cannot replace the public key either. It will not pass the check. Next feature is used is Unified Memory Architecture region, UMA region. For functioning, ME requires some piece of the RAM of the same RAM that the main CPU uses, and so it is important to protect that region of the RAM from accesses by the main CPU, because maybe CPU is running some malware, and that malware would look into the or change this code that is running on ME, and so Intel has implemented the protection feature. On boot, ME requests some memory from the BIOS. So BIOS reserves that memory from the RAM, and it turns on the log bit. And once this log bit is set, it cannot be cleared, and that memory region is accessible only by ME, and it cannot be accessed by the main CPU. So there used to be an attack that worked in 2009, but it has been fixed by Intel, and now you cannot access that region anymore. However, I thought, okay, I cannot access it at runtime, but maybe I can try accessing it using the cold boot attacks. So the first idea I had even did not involve the cold boot attack, but I just thought, since the locking of this memory region is done by the BIOS, maybe I can just patch the BIOS to not lock it and see what happens. So I had to spend quite some time reversing this memory initialization routines because it's very complicated with the modern memory. And then I disabled the code, which does set this log bit. I had to update the checksums because UEFI is very complicated. I reflashed, I rebooted, and I got a blank screen. So I'm not certain what happened, but I think the ME checks that this log bit is set, and if this log bit is not set, then it refuses to boot. So this approach did not work. Then I tried the actual cold boot attack. So here you can see the diagram. I have, for example, 2 memory sticks. And on the first boot, the UMA region is allocated. The code of ME is copied there, and it runs. And then I can try the cold boot attack, cool down the memory using the compressed air can, turn off the PC, quickly swap the sticks, turn it on, and if I'm lucky, if not too many time passed, the old code will be in the original memory stick. And because the memory location has changed, the new UMA region will be on the other stick. So I tried that many times, but I only got garbage. So for some reason, it didn't work. I discovered why later. So I tried, at first I thought maybe my memory is too high speed. It's decays too quickly. So I need to try lower speed. I bought some professional grade spray. I thought maybe my cheap compressed air is not good. It didn't work. And turns out that the memory, DDR3 memory that I'm using, it uses so-called scrambling feature. So it's not really to thwart the cold boot attacks, but it has this effect. So what they do, to reduce the interference between the signals, they apply some scrambling, and the memory content basically changes depending on the address lines, depending on in which memory slot it is, and also depending on the so-called scrambler seed, which is reinitialized on every boot. And so in this way, even if you take out your memory stick and put another PC, or you just swap them, when reading back, because the address is different, or maybe the scrambler seed is different, you get garbage back. So cold boot attacks against DDR3 are very difficult, and I was not successful in this. I had one more idea to use different size of UMA across different boots, because the size of UMA, which is requested by the ME from the BIOS, this is a field in the partition table, in the initial partition table of the ME region. And this partition table is not signed, actually. It is just protected by the checksum. And so I can change easily this field, this UMA size. And so I had this idea. First, ask from the BIOS a very big chunk of memory, 32 megabytes, boot. And so the ME will only use, of course, only 16 megabytes. And so it will be put in one part of the memory. And then on the next boot, reflash this FPT with 16 megabytes. So it will request only 16. So only 16 megabytes will be locked. And the other 16 megabytes that was used on the previous boot will be accessible. Unfortunately, this approach did not work either. Because it seems this scrambling seed is reinitialized. And so even though the memory remains, the data that you read is different. So this didn't work. Then I discovered that actually you can turn off this memory scrambling feature because it's a kind of an optimization thing to make your memory more reliable. It's not actually required for functioning. Now, in some boards, there is a BIOS setting. On my board, there was no such setting. So it seems that it's just hidden. The actual setting is still there. You just cannot access it from the BIOS setup screens. So there is a way to turn it on. I will not discuss it. I don't have time to discuss how I did it. You can check my previous presentation. I did similar thing. And so I could turn off this scrambling. Unfortunately, it still didn't work. I don't know what happened, but I'm still not successful in dumping this region. Okay, so yeah, I have some other ideas. I'm not ready to describe them yet, but unfortunately they need more effort, and I decided maybe there are other approaches that I can take. So I looked at all the firmware that I collected, and I found some which was a bit different from the rest. So there is so-called server platform services firmware, which is used on Intel servers board. So on servers board, server boards, there is ME as well, and it also runs some firmware, but it's different from the desktop firmware because they don't use most of the desktop features. They don't need overclocking, for example, and so on. So they use a different firmware. It has very reduced set of modules. The bring up and the kernel is still there. And when I looked at them, I found actually that bring up is not compressed, which was very nice because I could see the code and I could look at how it's implemented. And then I look at the kernel module, and it is also compressed. But in fact, this compression is trivial. It's not actually compressed. So it's just marked as compressed, but all the blocks are non-compressed. So I can just reconstruct those blocks and analyze them. So this was very useful progress. I could look at how those two modules are implemented. And there are some differences from the desktop, I guess, but still I can look at them. So, and then using those two modules and the boot ROM that I looked at, I could analyze one of the more high-level modules, which is named JOM in the firmware, but the actual marketing feature seems to be dynamic application loader. So it appeared in the MIS 7.1, and it allows actually to dynamically load and run new applications inside the management engine. So right now it's only used for Intel identity protection technology, for Intel IPT, but in theory it might allow you to run any kind of code inside. So I took a look at how it's implemented, And of course, first you look at what strings you have in the binary. And I can see these interesting strings: Java lang, out of memory error, VM server, and so on. So it looks like Java. So apparently, there is a Java virtual machine inside this module. And if I looked at the drivers, which I used, which use this Intel identity protection feature, there is a file with some base 64 encoded blob. And when I decode this blob, I actually see the manifest, which is very similar to the old manifest of the firmware, actually. So the format is a bit different, but it's still the same. And the payload is a file with signature Jeff, and the content seems to be some strings related to Java. So I looked at the opcode as well, but apparently opcodes are quite different from normal Java. So I decided to reverse this from the scratch, from this format. I spent quite a lot of time on it. But then I came upon this line in the source, in the binary: invalid constant offset in SLDC instruction. And I thought, what is this SLDC instruction? I don't see it in the Java specification. So let's ask Google. And yeah. And so I asked Google, and I actually get a document called the Jeff storage format. And so apparently, this Jeff format is a standard, and it's implemented. It was proposed in 2001, and it's actually has been accepted as an ISO standard. So this Jeff file describes a collection of several Java classes, and it's optimized for embedded applications. And so it was used by Intel to implement this Java applets inside the management engine. So once I had the specification, I found the specification on the internet. I wrote small disassembler in Python to decode this file. And then I looked at what those applets do, how they work. So there was no obfuscation implemented. So all the method names, all the variable names are there in plain code, plain text. So this was nice. Most of the Java is implemented in this same bytecode, and some native functions. It provides classes for cryptography, for UI elements, for accessing the flash, and so on. So for example, this is the interface which is used to implement the applets which are loaded inside. You can see that there are some methods that you can implement in this. And this is one of the applets that Intel provides for implementing the two-factor authentication. And you can see that it implements the method invoke command, on close, on init, and so on. So this is quite convenient, I guess, to write the applets for this management engine. However, these applets are, again, they're assigned. I cannot write my own. Well, I mean, I can write, but I cannot run them because the firmware will reject them. However, because there are many layers in this component, there may be some vulnerabilities. So just a bit about how it works. So Intel provides some DLLs that are used by the software which communicates with ME, which uses this identity protection feature. And so what these DLLs do, they send a request to the service which is running on your computer. So either over COM or TCP/IP. The service takes those requests, it serializes them. So they split into packets and send them to the ME over this host embedded control interface over the PCI to the ME. ME on its side parses those requests and passes them to this module, JOM module. JOM module parses the requests and decides to which applets they should go. And so then it comes to the applet, and for example, to that onCommand method, which does the actual work. And the reply goes in a different way. It goes over PCI to the service. Service unpacks the packets and passes back to the DLL, to the application. And this protocol allows you to send various sized buffers. So in theory, there may be a missing out-of-bounds check somewhere that would allow us to read or write memory, but I have not found one yet, but I'm working on it. Now, a little bit more about internal implementation of this module. So by looking at some strings, I discovered that Intel is using a so-called trusted execution environment, which is provided by the Trusted Logic Mobility company. They now got merged with some other, and they're called TrustSonic. So the software is called Trusted Foundations. And here is a small diagram from one of their flyers at how it works. So this platform allows to write you some applications. So in this case, these are applets provided by Intel. And they can run in this constrained environment, so-called trusted environment, inside the ME in this case. And so it protects the critical functionality from tampering by the host, by the malware, and so on. And this applets communicates with the host by using some secure channel. So in this case, this is the PCI communication, the host embedded control interface, but it may be some other. So some more thing about this trusted foundation software, that it's used not only in the Intel ME, but it's also used in several smartphones. And in those smartphones, it is using the ARM's trust zone functionality to separate the host OS, so the rich OS, and the secure part, which runs this trusted execution environment. Once again, because many of those smartphones, they run Android, and because of GPL, the code of the drivers must be open. And you can look at the source of the drivers, and actually there is a lot of similarity with the drivers used on the PCs, except on the PC drivers are closed source, but still you can match some code, and this is helpful. So protocol is not the same, because on PC it uses PCI communication, and on trust zone it uses shared memory. Because of that, the protocol is not the same, but there are lots of functionality, lots of functions which are similar, and so this is a very good source of information that you can look at and discover how it works. Now, a little bit about trusted execution environment. Actually, there is a specification released by the association called Global Platform. And this specification describes typical implementation of this trusted execution environment, such as client API, internal API, and so on, overall architecture. So it's not the exact match against what's running in the ME, but it's pretty close. So many of the parts were it seems many parts in this specification were taken from the implementation by Trusted Logic. So if you look at the specification and the code which is runs in the ME, it's helpful. It's a helpful reference. So the results so far. So my first presentation on this topic was called rootkit in your laptop. So unfortunately, I had to change the title because I still do not have rootkits. However, I think I'm making a very good progress because I'm understanding more and more of how the ME works inside of all the components. So, for example, now that I have the code of the boot ROM, of the bring up and the kernel modules, so I have almost the complete chain of the code which is being executed. So I have a complete picture of how it works inside. So I'm continuing to map many various APIs which I used in the modules. And I made this dumper for the Jeff classes, Jeff files, which allows me to see the implementation of the applets used in this dynamic application loader component. And also, one useful side effect of this was that I had to implement the support for ARC processor in IDA. And so this support was released in IDA 6.4 and improved in IDA 6.5. And so now everyone else can also start disassembling this firmware and look at how it works and how it's implemented, and so on. Now, what I'm planning to do next, I plan to work a bit more on this dynamic application loader because it seems to be a very promising direction. For example, maybe make a converter to the class files so that they can be decompiled using Java, because looking just at the bytecode is not very interesting. And document various protocols. Now the flash file system is a very useful source of information because most of the state is stored there, and so on. So it can be useful. Huffman compression, I mentioned that we still don't know how it works, but there is some hope in that area. I cannot talk about it right now, but hopefully we will solve it at some point soon. And also at the protocols, they're useful. Look at the protocols between ME and the host. There may be many vulnerabilities. BIOS reverse engineering is useful, and so on. Simulation, yes. Unfortunately, I ran out of time. If you are interested, you can catch me later and ask any questions. Thank you for listening. Sorry, actually, I have 3 more minutes. If you have questions, please ask now. Okay, thank you again.